All right, 11:10. So do people still have the link of the pad, recitation pad? Here it is. It says share link doesn't work. Sharing is unavailable this time. Let's see, how can I give you this link? Oh yeah, I see two people here. Let's see. Thanks, Thomas. Yeah, that's what I'm. Oh, wait. Three, 4, 5, 6, 7. Okay. Good. Okay, let me know if you still don't have the link. All right, we're gonna using this pad for this recitation again. Maybe I want to put a date on it. This third. MDP 2. So, okay, today we're gonna go over the two algorithms to solve MDP. And one is the value iteration, one is for graduate student, which is RTDP. So we're gonna running a kind of exhaustive example on value iterations, so folks can fully understand what they have to implement for the assignment. All right, so it's kind of just one line of code, right? So to update the value of each cell. So it's a dynamic programming. So the formula we want to use is the value of a state S is equal the reward of that state S plus some discount factor gamma, and the summation weighted summation from all the transitions of I think we're gonna take the max of actions and then S prime transition from current state, take an action S would lead us to a new state S prime. This T is the transition probability of that, and then times the utility of that state S prime. So that is the formula we're gonna use. And is that correct? I think so. If we goes to the let's see, if we goes to the the slides just to double check. Yeah, that's correct. All right. So, okay, we're gonna run an example on this. So assume we have a grid word, and then each cell is the, so let's make a big one. So each cell is a state. All right, we have 4 cells, so we have 4 state here. And so this is state 0, state 1, state 2, state 3. All right, and then each of them have this reward. So for state 0, it's a -1. For state 1, it's -10. For state 2, it's -1. For state 3, it's 0. And we know that state 3 is a terminal state. So this one is a terminal. Terminal state. All right, that's all we get. And then we have the model of the MDP. So this is very important. So for every MDP solver, we always assume we have the MDP model, which that we know this reward, and then we also know the transition probabilities. All right, so for each cell, it can goes to the neighbor cell. So for example, H0 can goes to state S1. Okay, this doesn't work very well. Let's see if I can do better. State S1, and then the transition probability would be, if you take the action from S0 to S1, it will have 0.9 probability end up in S1, but 0.1 probability end up in S2. All right, and then the other action is the same. So if we trying to move to S2, then we have 0.9 probability landing S2, and then have 0.1 probability landing as S1. So the same thing for each cell. You can either go to the neighbor. So for S1, it can goes to S0, and then it can goes to S3, and then for S3, it can goes, so S3 is essentially the terminal state, so there's no transitions, go back. But for S2, you can either goes to S0, and then, or you can goes to S3. So, all right. So yeah, let me put this clear. So for example, for S0, you have 2 actions. You can do action 0, which is goes to S1, and it will have 0.9 probability and the points S1, 0.9, and then have 0.1 probability goes into S2, and then you have the other action is to go down, A1, and then you will have 0.9 probability to be S2, and then 0.1 probability to be end up in S1. So all right, for each state we have these 2 actions. If you're following the action, there's a 0.9 probability landing the direction that the action pointing to. All right, everybody kind of understand the problem we want to solve? It's a very syntactic MDP here we are trying to solve. And then we want to find the optimal policy, which give us the maximize the total reward for us for each cell. All right. So okay, I'm gonna move to the next page. So here we want to solve this by using value iterations. First, VI, value iterations. All right. Okay, let's see what do we do here is so we have this 4 state, And then we have their values. We want to update the values by iterations, right? We have this for loop in the value iterations. So S0, S1, S2, S3, all right? So in time step 1, we initialize the value of each state to 0. So 0, 0, 0, 0. Right, and then we starting to, so this is a one line of for loop, right? So then we goes to time step 1, which we goes to the iteration 1, and then we plug in, you know, in the previous sheet we have this, in the previous pad we have this formula, we plug in this this formula. So yeah, maybe I want to share my screen so that this is actually recording. So we have this formula, right? And then we want to plug in this formula to compute our T1 here. So what we do is we plug in this. So when we want to compute S0, so let's see. So U of T1 of S0 is the reward of so it's the reward of this cell, which is -1. So yeah, maybe I will just leave this here so I can see. So it's a -1 plus, let's say we're using some gamma as 0.9. It's really 0.9, and then we have this max of we have two actions, so right, so we have the max of you know, and the first one is we take action 0, which have a 0.9 probability goes to S1. So it have action 1 have 0.9 probability goes to S1, and then the value of S1 here is you know, the value of S1 here, this one is 0, right? So 0.9 times 0 plus, so it's a summation, right? It's a summation over all the probabilities. It's a weighted utility by the probability. So it's have a 0.1 goes into S2. The value of S2 is also 0. So times 0. So that's for the first action. Then for the second action, going down from S0 is also you know, have 0.9 probability landing S2. The value is 0. So have 0.1 probability goes to S1. The value is also 0. Times 0. So it's you know, the max of 0 and 0 is 0. 0 times 0.9 is 0. So the value would be -1. For step 1, for the first iteration after we plug in the formula for S1, right? Does that make sense to people? It's essentially what you have to implement. If yes, please hit a 1. We're gonna do this trick again, so I know that you're actually following along. Okay.
I have a question.
Yeah.
What does the max mean again?
What is the max? It's the max of the weighted utility through all the actions.
Okay.
So you have two actions from S0, right? One is go left, one is go down. And then you take the weighted utility from there, and then you pick the max action. Here, I think it doesn't matter because both of them are 0.
All right, that makes sense.
Okay, cool. And we do this for all state, you know, for S1, as we can see here, if do we really, yeah, maybe we want to, let's see, for S1 here, because all the previous state is 0, so essentially the first iteration would just update the value to their reward. So for S1, it's I think it's -10. For S2, it's -1. For S3, it's 0, right? Because all the formula on this the transition part is all gonna be 0. So, all right, and then we do next iteration. At t times 2, we're gonna update S0, S1, S2, S3 by the previous utility. So that's S prime, right? So, and then in T3, we're gonna do this again until we converge. Converge means the maximum difference between two rows would be smaller than the epsilon you set. So that's the one of the parameter you have. So, all right, let's do one more iterations. Say, okay, let's see if this works. So, let's see, we have T2, T3, T until Tn. And then we have updated all these values all the way along. And then we have Tn have S0 equals 0, S1 equal 1, S2 equal -1, and then S0 equal 0. All right, and then we want to compute this Tn. Oh, this doesn't work. Tn plus 1. All right. For example, if we want to compute the S0 for that, so let's make this clear. So this value is from here. So right now we want to compute this value. I will put it there. So U of Tn plus 1 of S0 1 of S0 is, we're going to using the previous iteration, the value of the previous iteration to update this. So it's the reward, -1, plus the gamma is 0.9, right? And the max over the two actions. So the first action is transition into S1. So 0.9 times, which is 1, and let's see, 0.9 times 1, and then 0.1 goes into S2, which is -1. So 0.1 goes into -1. And then the other action is going down to 0.9 times -1 plus 0.1 times 1 times 1, right? So this will gives us 0.9 minus 0.1 is 0.8. This is -0.8, right? So this is 0.8. This is -0.8. So the larger one is the 0.8. So it's -1 plus 0.9 times 0.8 which is negative 0.28. So we have negative 0.28 here. The negative 0.28. Yeah. Negative 0. Why it doesn't work here? Yeah. It's clear. So this number comes from here. And we do that for all the time step t plus n until the difference between S0 of Tn and then Tn plus 1 is the absolute value is 0.28. If you have an epsilon value of 0.1, so you still have to go down to Tn plus 2 until you hit that all of the values of each of four state have a difference less than 0.1, you can stop. That's the value iterations. All right, and then you subtract your action from the value iteration. You say, okay, so for S, if we stop here at t minus 1, we know the action for S0 would be take the action of A1. Take the action of A1 because A1 has a larger reward in this formula. Does that make sense to people? If yes, please hit 1 in the chat so you know how to implement it.
Can I ask a question? Is the
Yes.
0.1 you talked about, is that just the input parameter, or does that have to be multiplied by gamma over gamma minus 1 or 1 minus gamma?
So which 0.1 are you talking about? You're talking about the transition probability?
No. I'm talking about the stopping criteria from the command line.
Oh, the stopping criteria is the difference between the previous iteration and current iteration for all the states. So
Okay,
the
so
result
it's
value.
delta.
Yes.
Okay.
So here for S0, it's 0 and then negative 0.8, then 0.28. So the difference is 0.28. So the absolute value of that is 0.28. So 0.28 is your difference for S0. And then you gather, you pick the maximum difference among all the state to see if that is less than the stop criteria. All right.
Okay. Thank you very much.
Yeah. So that's it. That's pretty much it. So it should be really easy to implement. Nothing complicated here.
So I have a question.
Yeah, sure. Go
Going
ahead.
off of what Francesco was saying, I saw in the lecture slides it said something about like multiply that maximum difference by gamma over 1 minus gamma.
Oh, really? We just
Yeah, if I remember correctly.
Okay, let's see. And stop.
But at the same, so you're totally right. But at the same time, in the PDF handout, I'm pretty sure it references stopping criteria as the difference. So that was my question.
Okay. Yeah, I think.
Or just the pure difference.
Yeah, it's an implementation variation. It's just different flavors of whatever works for you.
Okay.
You guys have the hand because you understand the algorithm. So you don't. The idea is to have you understand it.
Okay. Thank you.
Yeah. So yeah, feel free to try whatever variants you feel like it's more efficient for you. Yeah. Anyway. Okay. Cool. All right, that's the value iteration example we have. Then I'm gonna kind of quickly explain what is the RTDP. It is a more focused algorithm. It should be performed way more efficient than value iteration. So I goes to a new sheet, sheet 5. Then yeah, I think it's a 3 or 4 line of algorithm again. It should be not that. If I bring that up. Da-da-da. Yeah. So what you do is you go down the tree by picking a better value and then rolling a die on the nature. So that's the 2 things you're gonna do. So pick a better action and then rolling a die on the action to see what's transition the nature we're gonna pick, right? So you let's see if we can visualize this a little bit. So if you're in our initial state, okay, let's bring back the black. If you're in initial state, and then you have 3 actions, and then each action will have some probabilities, maybe 0.8 take you to some of the state, then 0.1 take you some of the state, 0.1 take you to some of the state, and then the other action also have this. What you do here is from the you first of all you initialize the value of each state to some initial value. I think Wheeler suggests 0, right? So either the upper bound. So in the implementation, it's a reward. So upper bound equals 0 for every state. So then you compute the value of this action by this weighted, the value of here, it's 0 times 0.8, 0 times 0.8, and then it's here, it's 0 times 0.1, 0 times 0.1, and then sum all of them, so it's still 0. And then the value for the second state, you compute it. The value for the third state, you compute it. You pick the best action. Right now, they are all 0, so it doesn't matter. So say you pick this action on the top, right? And then what you do is you roll a die right now. So you roll a die and here, and how can we visualize this? So you roll a die here, say because you picked this action regarding to the value. So pick this action, and then you roll a die here using the random number generator, and then the accumulative probabilities, right? So, and then say, okay, if the roll a die and a number in between 0 and 1, if the number is 0.5, the random number is 0.5, so it's landing this state here, I would say, right? So then you do the same thing for this state. So for this state, you have maybe two actions, and then this action have some transitions, and then you compute the values of these two actions, and then you select the one has a larger value. And then you roll a die among the transition probabilities, and then it will takes you to some state, and then from this state, you do it again. For the red thing, you pick the best action. For the blue thing here, you roll a die from the nature. It decides which state you transition into. You then go down until at some point, you transition into some state, and you pick an action, and it takes, and then you roll a die, whatever, and then it takes you to a state that is a terminal state. And then up until here, you can do your backup, So I think in the pseudocode, it mixed the backing up with the inside this rolling out. I think it doesn't matter where you do this line, inside the for loop or outside. So I do it like in the end. So I roll a die, pick action, roll a die, pick action, roll a die, pick action until I hit a terminal state. And then at this point, I starting to do backup. So I back up the value from here to let's see, to the state. So actually no. This is wrong. So the max of all the values of this action goes into this state, right? So and then here the same thing. You do all the way back up, and then this backups to this state. Then this value backs up to this state. So this is called backing up, and then you start the outside. This is called one trial, and then you do this trial until happy, which means you have a stop criteria for this. You know, you can do 600 or 500 or 1,000 trials. This is one trial. All right, the thing I simulate right now is one trial, and then you're starting to do the second trial. Like you keep swiping the tree from the left to right. Keep doing this, swiping the tree back up, swiping the tree back up, swiping the tree back up until you're happy. And then you're looking at each state to see what's the latest, what's the best action for that state is. That's your policy. All right, until you updated all the values, you can subtract you can get out your policy from the current value of each state. Does that make sense? If yes, hit 1. If not, please speak out loud. So I know you have a problem. Okay. Are we going to do out the example with RTDP? No, I don't think. So it's the same, right? We are at S0, and then we have, you know, 2 actions for S0, and then the action 1 would transition into S1 and S2 with 0.9 and 0.1, and then you pick an action. So because they are 0 at the initial, so you pick the action that has a larger value. So it's the same. It looks like the equation for the backups is different. It's the same. So here you back up the value of this action to S. What I do here is the yellow stuff. So you're backing up the value for this action to your state. So the U of this S equals to the action, the value of this action. So it's the same. It's this line here. But I take this outside this loop. You can do it right here inside the loop. Like when you do this, and then you update. It's the same. It will result in the same. Does that make sense to you, Connor? There's no mention of discount value in RTDP equation. Okay, that's an issue. Do we have to do discount here? Do we discount the future here in RTDP? Yeah, I think in the slides there's no discount value, but you might as well want to do discount. I forgot I do it or not. Feel free to try it with the discount or not. I don't think we need the discount actually for the, yeah, I don't think we need discount for RTDP here. Because you do the simulations, it will takes you to, let's see, it will takes you to the actions. Yeah, as long as it will eventually take us to a terminal state, it is fine. Yeah, you don't need the discount thing here. yeah, feel free to try the discount value here when you pick the actions, if you feel like you might need it in your implementation, but I don't think we need it. Okay. Cool. So if there's no more questions, that will do it for me for today. So yeah, I will keep all the pad notes here online. Feel free to look at it again. If you have confusion, post it on Piazza. We will try to answer your questions. Right. Cool. See you guys. Have a nice weekend.
Just one quick question before
Yes.
you
Yes.
go. What is the CSA term in the RDTP algorithm? In the
C.
backup equation, there's a term that's C of S and A.
Yeah. So that's essentially the reward of that state.
So where does A come into play there? If it's just the reward of that state.
The reward of that state, and then so I think we want to mention is the yeah. So it's I think it's just of the S. There's no A for C.
Okay. So
Yeah.
it's just the cost of the state.
Yeah, the cost of the state. Yes, but in some MDP formulations, the reward is associated to state action pair.
Okay.
Mentioned. Yeah, but in our assignment right now, it's very simplified. So the reward is only associated with the state. Okay. Cool. All right. Team, does that all make sense to you? Or do you still have questions?
I'm just struggling with having any real output that makes sense, even though I'm following the algorithm exactly.
So, all right, so I will suggest you to running your code on this example.
The sample?
Yeah, this one I share, I'm still sharing my screen. So do you following along with this example?
Yeah, I'm also doing it out by hand.
Yes.
And I'm not getting what I'm doing on paper. So I'm going to continue doing this out by hand. And
so this is the most simpler example among all those. So you do it by hand and then do it on your code and then debug each of this value to see why they are different.
Okay. I'll email you if I have any more problems.
Yes, yes, okay.
All right, thank you.
Yeah, no problem. Okay. All right, bye guys.